May 1946, Aberdeen Proving Ground. American Ordnance officers rolled a captured Panther onto the test line, not to mock it, but to measure it. The tank was stripped, gauged and fired, its components logged with the clinical patience of scientists. Germany's most feared medium had become a classroom on tracks. What stunned observers first was performance on paper turned into performance on range. The Panther's 7.5mm KWK-42 L70, a high-velocity gun designed for long-range killing power, could defeat heavy armor at combat distances that humbled Allied crews in 1944. Sloped glacis, refined optics, and a balanced silhouette advertised a design philosophy learned the hard way on the Eastern Front. Production totals in the thousands had made it ubiquitous. Battlefield reputation had made it notorious. Yet the test line also exposed the price of that excellence. Complex transmission trains and maintenance-intensive running gear buckled under sustained use. Fuel thirst and fragile driveline elements undermined the elegant geometry of its armor. The Americans took notes with a pragmatist's eye. Keep the slope and the velocity. Lose the brittleness and the over-engineering. The deeper shock belonged to the Panther's creators. Under post-war supervision, German engineers arrived to find former enemies asking precise, collegial questions about alloys, heat treatment, and site geometry. The role reversal was unmistakable. The United States, victor by industry and logistics, now sought lessons from the Reich's premier tank, openly, methodically, and without propaganda, by summer's end. The conclusion was simple and audacious. Data, not myth, drove decisions. America would not copy the Panther. It would surpass it by extracting principles and discarding flaws. The real question no longer lingered over whether the Panther had been formidable. It was how quickly American engineers could transform its strengths into their own decisive advantage. By 1944, Germany's Panther had achieved near-mythic status among panzer crews. Born from the shock of encountering the Soviet T-34 at Mtsensk in 1941, it represented a technological revenge. Steeply sloped armor to deflect incoming fire. A long-barreled 7.5mm K2K-42 gun capable of piercing 138 millimeters of steel at a kilometer, and optics that could track a target through dust and dusk alike. The Wehrmacht called it the ideal Panzer, while Inspector of Armored Troops Heinz Guderian boasted, "The Panther has no equal in firepower or armor balance." Official German production logs from the Bundesarchiv show that over 6,000 Panthers were built between 1943 and 1945, most rolling off assembly lines at MAN and Daimler-Benz. They spearheaded panzer divisions from Kursk to Normandy. At Kursk alone, after-action summaries from the 39th Panzer Regiment claimed 5 enemy tanks destroyed for every Panther lost, a statistic that echoed through propaganda bulletins and training schools alike. Against Western allies, the legend only deepened. British AFVT evaluation reports from 1944 described the Panther as formidably gunned and effectively protected. American tank crews who first faced them near Aachen reported being destroyed at twice their own effective range. Every engagement confirmed German doctrine that superior design would outweigh numerical inferiority. Captured radio intercepts from December 1944 reveal the arrogance this confidence bred. One SS Panzer commander sneered, "The Americans build tractors, not tanks." On paper, he wasn't wrong. Allied intelligence at the time conceded German superiority in armor and guns. But beneath that confidence lurked fatal complacency. The Panther's technical brilliance depended on perfect conditions, skilled crews, unbroken supply chains, and mechanics who could maintain its complex transmission. By late 1944, those conditions were crumbling. Yet inside design offices and field headquarters, faith in engineering perfection persisted, even as factories fell silent under Allied bombs. The Panther had become a national symbol of genius and hubris, while the Wehrmacht still celebrated its invincible cat. American ordnance files already recorded a different reality. The era of mechanical artistry was ending, and the age of practical ingenuity was about to begin. In 1944, the United States faced the battlefield with a tank that seemed hopelessly outclassed. The M4 Sherman, rugged, reliable, and numerically supreme, was derided even by its own crews as a Ronson, the lighter that lights every time. Comparative firing trials from the U.S. Ordnance Department left no illusions. The German Panther's long 75mm gun could pierce 138mm of armor at 1,000 meters. The Sherman's 75mm managed barely 88. On the front lines, the imbalance felt personal. Lieutenant Richard Long of the 3rd Armored Division wrote in his diary, "They can hit us before we can even see them." Official reports from Fort Knox admitted the shortfall. Enemy tanks exhibit superior gunnery and protection. Our advantages remain mobility and numbers, noted the 1944 Equipment Review Board. The British AFVT 37 report confirmed similar findings after Normandy. The Sherman required a flank shot to kill a Panther frontally at less than 600 yards. Such figures bred fatalism among Allied crews and skepticism among foreign observers. Yet behind the defeatist headlines lay a quiet revolution in mindset. American engineers, logisticians, and tacticians understood something their adversaries often forgot. Wars are won by machines that reach the battlefield, not by prototypes that break down on it. Production records from Detroit Arsenal show over 48,000 Shermans built by 1945, each standardized for rapid repair and global shipment. When Panthers froze on the Ardennes roads, Shermans kept moving. Diplomatic correspondence between London and Washington even records British pleas for heavier armor, only for US officials to reply that shipping capacity, not ambition, dictated design. The inferior tank, derided for its simplicity, was the only one that could cross oceans in pieces and roll off ships ready for combat. On paper, America was the underdog, outgunned, out-armored, and underestimated. But within supply depots and design bureaus, the real contest had already shifted from metallurgy to mathematics, from elegance to endurance. And when captured Panthers began arriving at Aberdeen, those quiet pragmatists saw not humiliation, but opportunity. While the war's victors celebrated parades, America's ordnance engineers were already at work turning defeat into instruction. At Aberdeen Proving Ground, rows of captured Panthers waited under the Maryland sun, each tagged, photographed, and stripped with scientific precision. The goal was not imitation, but extraction, to learn every secret. Germany's engineers had hidden in steel. Declassified memoranda from August 1945 show the U.S. Army's deliberate plan to harvest knowledge before the Cold War even had a name. All foreign armored vehicles of technical significance will be studied for material and tactical application, read Directive 2/1845. Under Lieutenant Colonel John K. Thompson, teams from the Ordnance Department and the Detroit Arsenal began a component-by-component analysis. They recorded gun tube metallurgy, slope angles, and suspension stress tolerances. Thompson's handwritten margin note survives. German gun design is years ahead in metallurgy. American optics lagged 2 generations. Within months, results flowed into American prototypes. Fort Knox torsion bar experiments confirmed the Panther's smoother ride and steadier gun platform compared with the Sherman's vertical volute system. Engineers adapted the principle for the T-26 E3 Pershing, reducing recoil dispersion by nearly 30% in tests. The Aberdeen Metallurgical Section dissected a Panther glacis plate, identifying manganese content that produced exceptional hardness without brittleness, a discovery immediately applied to the Pershing's armor program. Yet the U.S. innovators refused to repeat Germany's obsession with complexity. Thompson's final 1946 report stated bluntly, "The Panther is a magnificent weapon when it runs. We build tanks to cross continents, not parade grounds." That sentence crystallized the new American doctrine: simplify to multiply. Every design meeting balanced battlefield performance with logistic reality, how quickly it could be produced, repaired, and shipped. By early 1947, Panther lessons had filtered into the M46 Patton. Sloped armor geometry, improved 90mm ballistics, and torsion bar stability all bore traces of the German cat, but refined through American pragmatism. A captured German engineer, when shown Patton blueprints, admitted in disbelief, "You have taken our ideas and made them work." In that moment, the balance of design genius shifted irreversibly. The secret strategy was never to copy the Panther, it was to mine its brilliance and eliminate its weakness. What Germany had built as a masterpiece of engineering, America reforged into a system of victory. By late 1946, Aberdeen's proving fields resembled an open-air laboratory of enemy technology. Freight cars arrived from Antwerp carrying 7 captured Panther tanks, their hulls still dusted with the mud of the Ruhr. Each was unloaded, catalogued, and photographed before being towed into disassembly sheds marked Foreign Materiel Division. Technicians logged over 1,500 photographs and hundreds of blueprint tracings, every hinge, bearing, and weld recorded for analysis. The U.S. Army Ordnance Office maintained a quiet but methodical pace. German engineers, once fated by the Reich, were now employees of their former enemy. Under Operation Paperclip, 6 Panther designers from MAN and Daimler-Benz were interrogated, debriefed, and offered civilian contracts. One recalled later, "They showed us the Pershing blueprints as if we were colleagues." The Americans sought not to humiliate, but to understand. Every session revolved around a single question: how had Germany built a tank so lethal yet so fragile? Colonel Robert Ix of the Ordnance Division described the atmosphere in a 1947 memo. No idea was sacred if it served improvement. Engineers compared blueprints, tested tolerances, and charted design parallels between the Panther's 75mm turret and emerging 90mm US gun mounts. For the first time, industrial rivalry turned into collaborative reverse engineering. As testing continued, logistical teams recorded detailed performance data, gearbox endurance, torsion bar fatigue, and cooling system efficiency. At Fort Knox, experimental models incorporating Panther suspension geometry ran 500-mile field tests across Kentucky terrain, proving the concept workable under American maintenance standards. To the German visitors, this openness was bewildering. They had lived in a system where secrecy equaled survival. Now their designs were discussed openly in American workshops, dissected without arrogance, improved without hesitation. By spring 1947, the groundwork was complete. America had not merely captured enemy machines, it had captured their philosophy. The next stage would reveal how quickly that philosophy could be transformed into a weapon of its own design. February 1947, Aberdeen's firing range roared back to life. Engineers and officers stood shoulder to shoulder as 2 tanks faced each other across the cold Maryland plain, the captured German Panther and America's M26 Pershing. The test wasn't symbolic, it was scientific. Rangefinders clicked, wind speed logged, and ballistic plates mounted. This was the showdown of philosophies, precision versus pragmatism. The first round came from the Panther's famed 7.5 cm KWK-42, its long barrel flashing with surgical sharpness. The shell tore through the test plate at 1,000 meters, punching cleanly through 138 millimeters of rolled armor. The observers nodded, performance as advertised. Then the Pershing's 90mm M3 thundered in reply. Its armor-piercing round not only matched penetration, it exceeded it, cutting through 150 millimeters at the same distance. Lieutenant Colonel John K. Thompson scribbled into his field log, "The Germans appeared stunned that we had already matched their ballistics." From that moment, the myth of German invincibility began to fracture. Aberdeen's technical summary concluded that American firepower had achieved parity, and its delivery systems, simpler, lighter, easier to maintain, were already superior. Mechanical endurance trials deepened the contrast. The Pershing completed 500 miles without major component failure. The Panther's gearbox seized after 150 kilometers. Engineers annotated it dryly. Maintenance, impractical under campaign conditions. The psychological reversal was immediate. Former MAN engineers brought to witness the trials watched in silence as their creation, once the terror of the Eastern Front, met its equal in an American machine conceived in the chaos of 1944. One murmured, "You learned faster than we ever did." What began as curiosity had evolved into mastery. By spring, Ordnance memos circulated with a new directive. We defeated them in production. Now we must defeat them in design. The next evolution, codenamed Patton, would embody every lesson Aberdeen had uncovered. Sloped armor refined from the Panther, torsion bar suspension adapted for field service, and a powertrain built for global warfare. The tests proved more than ballistic equivalence. They revealed a cultural triumph. German perfectionism had birthed brilliance too fragile for real war. American pragmatism turned borrowed brilliance into lasting power. Under the thunder of those guns, the baton of armored supremacy passed quietly, from a ruined Reich to a rising superpower. When the firing trials ended, the real revelation began, not on the range but in the workshops. Aberdeen's mechanical crews logged failures that exposed the hidden weaknesses behind the Panther's elegance. Within 150 kilometers of testing, transmission gears stripped, final drives cracked, and cooling systems overheated. American logs recorded the results bluntly. Maintenance, prohibitive in campaign conditions. For the first time, the myth of German mechanical infallibility had data to contradict it. Under Operation Paperclip, the Panther's original designers were brought to observe the post-trial analysis. They watched as American engineers dismantled entire assemblies in minutes, without special tools, without factory precision. The visitors were stunned. Their own manuals required field depots and specialists for tasks American soldiers performed under canvas tents. In OSS interrogation summary, WWII 2048, one-man engineer confessed, "They out-engineered us by refusing to worship complexity." The cultural reversal was profound. The same men who once lectured Allied officers on German design superiority now took notes from ordnance sergeants explaining how to swap a gearbox with a chain hoist. The Panther, they realized, was a weapon built for a perfect war Germany could no longer fight. America built for the imperfect one it actually faced. Paperclip reports record genuine astonishment when Germans examined the M26's simplified cooling and power systems. One designer admitted, "We spent months reducing drag in fan housings. They improved it in a week," another commented. "You learned faster than we ever did." What had begun as defeat now became reluctant admiration. By summer 1947, the shock had matured into recognition. The Reich's engineering philosophy, precision at any cost, had collapsed under the weight of its own perfectionism. The Americans had proven that the greatest sophistication lies in simplicity. When Aberdeen's gates closed that year, Germany's best designers departed humbled, leaving behind their disassembled masterpiece and the blueprint of the next generation of American armor. The Aberdeen findings moved swiftly from laboratory to policy. By autumn 1947, the Ordnance Committee had issued Directive 347. Every new tank would combine German lessons with American production discipline. Armor board records show engineers sketching Pershing hulls beside Panther blueprints and annotating them with simpler layouts. Out of those drawings emerged the M46 Patton, sloped armor refined from the Panther, torsion bar suspension adapted for field service, and a reliable Continental engine replacing Germany's delicate Maybach. Production began in 1949. Barely 4 years after the first Panther arrived at Aberdeen. Strategically, the evaluation shifted how Washington and its allies viewed technology itself. The G2 Bulletin of April 1948 called the Panther study the benchmark for future enemy analysis. American intelligence teams now approached Soviet equipment with the same methodical curiosity once reserved for German machines. In the newly forming NATO, British and US designers shared Panther data to harmonize armor standards and optical systems, laying the foundation for joint Western armament policy. The Royal Tank Design Board's notes from 1949 list U.S. Aberdeen slope angle findings as reference material for the Centurion Miko-3. On the home front, American newspapers ran stories with headlines like "Enemy Technology Turns Teacher." The public, once worried about inferior tanks, now saw proof that American ingenuity could absorb and improve on its enemy's best. Photographs from Aberdeen tours show visitors standing beside a captured Panther display placard reading, "From adversary to instructor." The symbolism was unmistakable. Within the Army, the doctrinal impact was equally profound. Training manuals from Fort Knox, 1949, introduced the concept of maintenance as firepower, a philosophy born from the Panther's fragility. Colonel Robert Hicks summed it up. "The Panther taught us where to add strength and where to simplify." Even research funding shifted toward durability testing and crew ergonomics, rather than exotic mechanisms. By the time the first Pattons rolled into service, German design principles had been transformed into an American language of efficiency. As Chief of Ordnance Gladian Barnes declared in 1948, "Captured science has become our insurance for the future." The impact was immediate, but its consequences would echo through every armored division of the Cold War. When the Aberdeen sheds finally emptied, their impact continued in classrooms and command posts across the Western world. At Fort Knox's Armor School, the first post-war training manuals opened with a chapter titled "Lessons from German Armored Warfare." Cadets studied the Panther's geometry, its torsion bar stability, and its downfall through over-engineering. Instructors hammered home the moral, "Simplicity is survivability." By 1950, that lesson had become doctrine embedded in Armor School Manual TRA 24 and echoed through every gunnery range in America, Ordnance Historical Study. Number 22 traced the direct genetic line from the Panther to the Patton series. The M46 carried its sloped armor and torsion bar layout. The M47 refined its turret profile. The M48 and M60 extended its philosophy into the jet age with cast armor and stabilized guns. By the time the M60 entered service in 1960, American designers openly acknowledged that the seed of modern tank design had sprouted from a German hull disassembled at Aberdeen 13 years earlier. Across the Atlantic, NATO's 1952 Armament Standardization Conference adopted the same principles. French, British and Italian engineers agreed on sloped armor angles and optical sight placement based on US test data from the Panther. At Shrivenham, lecturers referred to the Aberdeen model as proof that technical intelligence could bridge enemies into allies. What had begun as salvage became the foundation for collective Western armored doctrine. Historians later recognized a deeper legacy. Dr. Stephen Zaloga called the Panther the most influential tank America never built, and the Royal Military College summed it more dryly. Every Patton owes its lineage to Aberdeen's foreign cat. Yet the story was never one of imitation. The U.S. Army had transformed a defeated enemy's technology into a self-reliant philosophy of innovation. From the Panther's steel came the template for the modern main battle tank, balanced firepower, mobility, and maintainability in one machine. Even the Cold War's strategic culture bore its mark. Intelligence units that once examined Panther gearboxes would later study Soviet T-54s and T-62s with the same dispassionate precision, repeating the lesson that understanding the enemy was the surest path to superiority. In museums at Aberdeen, Bovington and Munster, surviving Panthers stand as silent mentors, reminders that knowledge, even won from war, is the most enduring weapon of all. From the wreckage of a defeated empire, American engineers forged a century of armored dominance. The Panther's story did not end in the Ruhr. It continued in Detroit, in Kentucky, and on every NATO training field where its lessons still rumble beneath the treads of modern steel. When the last Panther hull at Aberdeen was sealed under museum glass in 1948, it symbolized more than the end of a study. It marked the beginning of a doctrine. What had started as an autopsy of a defeated enemy's masterpiece became the blueprint for America's rise to armored preeminence. From the M46 Patton onward, every U.S. tank carried invisible traces of that captured machine, the slope of its armor, the rhythm of its suspension, and most importantly, the philosophy behind its creation. Colonel Robert Ickes summarized it best in his 1949 memorandum. The greatest weapon is curiosity. It was curiosity that led American engineers to look beneath enemy steel rather than simply celebrate victory. It was discipline that turned what they found into the practical, durable designs that would dominate the next 50 years. The Patton, the M60, and even the modern Abrams trace their lineage not to imitation, but to understanding. By 1950, the Armor School taught cadets to study your enemy, not to copy him, but to surpass him. That principle outlasted the war that inspired it. Every subsequent generation of American tankers, on the plains of Korea, the deserts of Kuwait, or the fields of Europe, has benefited from that single revelation born at Aberdeen, that innovation begins with listening to the lessons of defeat. Today, historians still point to those quiet days in Maryland when the engineers of two former enemies stood side by side, united not by ideology, but by respect for machinery and mastery. Out of that unlikely partnership came not just superior tanks, but a philosophy of progress that defines the American way of war. In the end, the Panther did not die in defeat. It lived on as a teacher, and its greatest lesson endures: knowledge once captured belongs to the future.